It doesn't have a name, it's just the U.S. engineering baptism. Okay, thank you. Thanks, Anka. Okay, so we have two vectors here, and we are acting on the point P. So basically, two vectors, F1 and F2, and I want to find this vector we're calling F3. We don't know it. Even though it's drawn in there, we don't know what it is. Basically, to make sure that this point, this whole graph is in equilibrium. What equilibrium means is, imagine that we have a tug-of-war going on. We have three teams. Here's team 1, here's team 2, and here's team 3. If all these teams pull, and let's say this is the ball in the middle, if that ball doesn't move, then what that means is that we're all in equilibrium, right? Say this is a tug-of-war with three teams. If we have that ball in the middle not moving, it's in equilibrium. We want to figure out what value, what team 3 needs to pull with to make sure that that ball doesn't move. Does that make the question clear? Okay, good. Thanks. Thanks, Louise. I appreciate you answering me. Okay, so how do we find the force? How do we find what the force is that F1 is? What the force is that F1 has? We have to break it into its component vectors. Let's see. Michael W., you want to do this one? Okay. You can put your mic on if you want. You can't. Okay, no problem. So, how would I find vector F1? Exactly. So I have the x value is going to be 4.5 cosine of 64. Kind of. We'll talk about that, the rest of it in a minute. And then what else? That's the x value. We'll do it like that. And the y value would be 4.5 sine of 64. The only thing is there's one thing missing. Do you know what it is, Michael? Does anybody know what it is? X is negative, right? It's in quadrant 2. So the x value is negative. Okay? That's the only thing. Other than that, perfect. And then how do I find the magnitude of F2? Or the vector F2? Good. 6.3 cosine of 18, comma, 6.3 sine of 18. Yep. Perfect. So those are my two vectors. Does anybody have the values that go with it? I should go get my phone. Does anybody have a calculator with them or no? You do? Could you tell me what those values are? I'm sorry. F2 is 6, comma 2. Okay. F1 is, let's just round it off to -2, comma 4. Okay? Good, thank you. So now, if I add these two vectors together, we get 4, comma 6, right? So if I add these two vectors together, I get 1, 2, 3, 4, 1. So my resulting vector is that vector, right? So we know that the teams F1 and F2 are pulling with this force, this magnitude, and in that direction. So if I want to make the whole thing not move, right? Remember, I want to make this whole thing not move. What I need to do is I need to pull on this, on the team 3 has to pull in the equal and opposite direction. So F3 needs to be -4, -4, -6. That all make sense? All right, good. Is there any questions about this? All right. All right, this one's a little bit more complicated. Let me see if I can break this down. So we have this 850-pound object on a ramp, okay? And the incline is 25 degrees. And what I would need to do is find the force to hold the object stationary in equilibrium. So basically, I want to know what this force is, right? Does everybody understand that? Because right now it's going to slide down the ramp. So I need to have some kind of person standing there holding it, or a chain or something. We want to know what the force is that I need to be able to counteract that sliding down the incline. Okay? So let's see what we can see. I know that this angle is 25 degrees. And I know that, let's see, I'm trying to think of how I'm going to draw it so I can make it really clear. Well, if this angle, that's a right angle, so that means this angle right here has got to be 65, right? So if that angle is 65, then, let me see how to explain it. There's a little bit of geometry here. So I have, let me see if I can redraw it and make it a little more clear. So this is 25, this is 65, and this is 90, right? Then I have, if this is 65, and this is 90, then, let's see, how can I say it? Okay, here, I'll do this. I can also say that we can move this triangle down, so that means that this angle right here is 65, and this is a right angle. So basically what I'm trying to say is that the angle that this angle right here, angle G, is also 25 degrees. Does everybody see how that's 25 degrees as well? Okay, good. Very good, thank you. All right, so I have this triangle, and what I want to do is I want to find if I find this right here, then the opposite will be what I need. So that's the composition of G onto vector V. So I have the composition of G onto V. And that is equal to, okay, let's see. So we have, well, let's write the formula. We have G dot V over V squared, the magnitude of V squared, times vector V, right? Also, wait, let me see if there's a better way. It's 50. Yeah, let's just pull this triangle out. I think we can do it like this. Here's my triangle. Here's my right angle. I know this angle right here is G, and it's 25 degrees. 25 degrees, sorry. I know this is 850 pounds, and basically what I'm trying to find is, let's call it Y. Isn't that true? Okay, so now this one's pretty easy because I can just say we don't even need this formula because I don't really need the direction. I just need the magnitude. So I can say this is equal to the sine of 25 degrees is equal to Y over 850. So that means that Y is equal to 850 times the sine of 25 degrees. Right? Okay. That's it? 35 pounds? 36 pounds. So it only takes 36 pounds to hold this 850-pound object up. Really? All right. Well, it looks like that's it. Is it wrong? Okay, that seemed wrong. 360. Okay, that feels much better. 360. Yeah, thank you. Pounds. So yeah, I didn't think I'd be strong enough to hold that up. Okay, so 360 pounds. So if I have a chain that can hold 360 pounds, then that won't. Okay, understand. Okay, so does everybody understand this? I know the geometry is probably a little funky, but other than that. Any questions here? I think we're almost done. Let me just see if anything else is left here.